Good afternoon, this is Schweitzer, and I'm going to cover a couple of things here, starting our chapter on equilibrium now. We've already done Ka and Kb in our chapter on acids and bases. So some of this is going to be tagging on to that particular conversation. So remember that when we're making something, there are some processes that go only to product, which would be something that is called completion. This is your typical standard stoichiometry. If you're a person who buys parts for GM and you're making cars, then that person would have to have the parts available to make all the cars. And I imagine that would be probably a fairly stressful job, in the fact that if a part runs out, then the whole line stops and GM's no longer making cars. There's no one in GM that's dismantling cars. This is not necessarily the case if you're looking at a company that makes ibuprofen. Now, the majority of ibuprofen is made outside of Dallas, and they're taking chemicals, carbon, hydrogen, oxygen, some other ones, probably nitrogen, and they're making, through a chemical process, ibuprofen. And in this case, all chemical processes have forward and reverse processes. Not all of them, but lots of them do. So the overall goal of equilibrium is to figure out how much actual ibuprofen I'm going to get based on the amount of starting material I have. So none of the reactions we're speaking of here are not going to be going to completion. So that's our overall goal. Keep that in mind. Why do we care about equilibrium? Because in this sense, it tells me how much product I'm actually going to get. Same as stoichiometry. And if you know this purpose in mind, it makes it more worthwhile to do the math and figure it out, because ultimately that would be a substance which maybe you could sell for a profit. Alright, so let's look at how Kc varies from how Ka was. Well, Kc is any reaction that we're tracking concentrations. Very important. We're tracking concentrations. If it doesn't have a concentration, then it's not trackable. Things that do not have concentrations are pure solids and pure liquids. These would have a symbol S and a symbol L. So let's try out just a common example. Let's go 1A plus, and let's make this thing an aqueous compound. 2B, we'll make this guy a liquid, plus 3C, we'll make this a gas, goes to 4D, let's make this thing a solid, plus let's go with 5Fs, and let's make F, let's make it another aqueous compound. Okay, so now I want to write out what's called my equilibrium expression. Let's take a quick side note to just remember what does that mean. Equilibrium expression is a calculation of K. K is a ratio of product concentrations over reactant concentration. You'll see it's got a slight variation how you actually calculate, but that's the general idea. And reactant concentrations going to product concentrations. When we get to our stalemate or our endpoint, if we have more product than reactant, then we are K is greater than 1, and we are product favored. If we're in the middle, then they're equal, and we're right balanced. Neither products nor reactants would be favored. The concentrations of my product reactants would equal the concentration of my products. And if we're on this side, it would be product, the K would be less than 1, and it would be considered reactant favored. Alright, so how do I write this out with this thing? Well, again, I cannot track solids and liquids, so my K expression equals the concentration of F. Now F is an aqueous compound, so at this point I'll go here and I'll put a 5 up top because that's the coefficient. Cannot include D. So that's it for this guy. A, I have concentration of A to the first times the concentration of B. B is a pure liquid, cannot include B, pure liquid. And then concentration of C is a gas. Now gases, they have volumes, they have moles, so they can easily be converted to moles per liter. There we go. This is the equilibrium expression for that particular process. When we say Kc, means all we're doing is we're tracking concentrations. Okay, next up, an alternate way that we can track things. In this case, we're tracking concentrations. So Kc tracks concentrations. But is there an alternate way? And that is true, there is, and we would call this Kp. Alright? And this tracks what we call partial pressures. So we'll take a little moment here and well, let's write out the Kp expression first. So, and then we'll talk a little bit about partial pressures. So this thing tracks the pressures or the partial pressures of gases. So really we can only include gases. So my Kp equals, and on my product side I don't have any gases. So I'm just going to put a 1 there. And then my reactant side I only have one gas, and that is C. So this is the way we write this. P, lowercase p, parentheses, unlike the bracket which meant molarity, and then put C in here, and then I'm going to put cubed, like that. And this is the Kp for this particular reaction. So let's take a side moment here, remind ourselves if we don't remember or if we didn't by chance know, what is a partial pressure? Okay. Well, let's say we have a box. Now I'm going to have this box, and this box is a rigid container box. Contains X, Y, 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 and Y. Now I'm going to take that X out. I'm going to go call it Z. Okay. So in this case, the box is 2 liters in size. Let's just say the box has a total pressure of let's go 2 atmospheres. And let's say we're at 273 degrees Celsius. Okay, so in this case, you should note that the pressure inside this container is due to collisions with the inside container of the wall. So every time something bounces off the container, the wall, we get a collision, and that will eventually have a total collisions, which will eventually give us our total pressure. Okay, so inside this thing we have lots of collisions, but for Z, 1/5 of the particles are Z, and for Y, 4/5 of the particles are in fact Y. So in this case, we call this, which is going to be this guy right here, is commonly just calculated as by what we call mole fraction. Mole fraction is moles of Z divided by total moles, and it'd be, we don't multiply by 100, but if we did, we call it mole percent. So just mole fraction. And of course, if you're doing mole percent and you wanted to say, okay, what's the total pressure contributed by Z, then you just divide by 100 to get to mole fraction and then multiply. So we're going to take this guy, 1 divided by 5 is 0.2, multiply this times the 2 atmospheres, and this is going to give us, in this case, 1/5 of 0.2 is 0.4, and it's in atmospheres. And then this guy is just going to be 0.8, 4 divided by 5, 0.8, times 2 atmospheres, total pressure, gives me 1.6 atmospheres. We call this the partial pressures. Now add them up nicely, you get back to 2 atmospheres. This whole process here is commonly referred to as Dalton's law of partial pressures. Okay. Now, all right, great. So we know that X has a partial pressure of 0.4, I should say Z has a partial pressure of 0.4. Okay. So this is what we're actually tracking. The partial pressure of Z is 0.4. The partial pressure of Y is 1.6. And that's what we're tracking. Now, you should be aware that this 0.4 could also be calculated via Pivner. PV equals nRT. If I put in just the moles of Z, then I'm just going to get just the pressure of just Z, which is the partial pressure. I should be aware. If I were to put in the total moles, then I would get the total pressure. So in this case, pressure equals nRT over V. And if I want the partial pressure of just Z, that's fine. I need the moles of Z. I would use this guy, which is 0.0821. The temperature in this case is 273. And the volume in this situation is 2 liters. So the only things that are affecting the partial pressure of Z would be the number of moles of Z, the temperature here, and the volume. Those are the things that are going to affect Z. So let's try another example. I got my same box. Same exact everything, okay? And I have a Z, 1, 2, 3, 4, 5. But this time I'm adding into this thing 1, 2, 3, 4, 5. 5 new particles. The volume is 2 liters. The temperature is 273. But now, what's my new pressure? You should note that I have twice the number of particles. Therefore, if you do a Pivner calculation, new pressure would be 4 atmospheres. Okay. All right. Now, let's compare that to another container. Okay. Another container. Now I'm going to take this same box. Okay. And I'm going to cut it in half. Okay. Now this box, I just have my regular Z and my 4 Ys. Now in this situation, okay, my volume is now 1 liter. Temperature, 273. What's my new pressure? Well, you should know, either via Pivner or via combined gas law, that if I cut my volume in half, my pressure should double. It was 2 liters, 2 atmospheres to begin with. Now it's up to 4 atmospheres. Same as the one above it. The top one went up because I added gas. The bottom went up because I cut the volume in half, doubling my pressure. What can I say about the partial pressures of these individuals? Okay. Now this guy, the top one, you should be aware that the partial pressure of Z is still 0.4. The partial pressure of Y is still 1.6. Why? Well, P equals nRT over V. You could calculate it if you want. Easy enough. Put in your moles, put in your temperature, put in your volume, which is all provided. The moles are not provided, but you could calculate it out. Nothing here has changed. All I did was add more particles that weren't Z or Y, and therefore my partial pressure of Z and Y did not change. I would have to add another partial pressure of circle, which equal 2 atmospheres, giving me a total pressure of 4 atmospheres. In this situation, my partial pressure of Z and my partial pressure of Y. Well, in this situation, the partial pressure of Z is equal to the moles, which has not changed. R has not changed. Temperature has not changed. But my volume is now 1/2 of what it normally was. So my partial pressure is going to double. Same numerator, half the denominator, this doubles. My new partial pressure is 0.8. And this partial pressure is 3.2, giving me a total pressure of 4 atmospheres. Okay. Now again, this is just, we're tracking partial pressures. And this is what we'll be doing. You need a little knowledge to be able to work through this. Let's look at our first page in our Alright, so here's a example of a workbook page. I will run through some of these with you here. Alright, so methane, I'm going to write this out here. CH4 is methane plus O2 would be 2 O2s when I balance it, producing carbon dioxide plus 2 H2Os. Initial stoichiometric ratio at equilibrium or ending point. 5 grams, get rid of grams and go to moles. 1 mole is, if you add the molar mass, is 16 grams. 0.031 is our moles. So this is 0.031. The oxygen in the atmosphere, at least, is not going to change concentration or be really consumed. So this is going to be an excess. We will lose 0.031, go to 0. This is not equilibrium but completion. I will lose 0.062 of that guy, gain 0.032, and I will gain 0.062. In the end, do all arithmetic. I don't know how much I have left, 0.032 and 0.062. Notice the stoichiometric ratio matches 1, 2, 1, 2, 0.032, point double, single, double, so make sure you know that that S stands for stoichiometric ratio. Whenever we're gaining and losing things, it is via the stoichiometric ratio. So at this point, let's sketch this out. I'm just going to mark, this is time by the way, I'm going to mark a time which I'm going to just, for my own self, when I'm going to have things run out. It runs out at that time. So this methane is going to run down to that, at that point it hits 0. The CO2 and the H2O are going to both increase, but they will not change beyond this point. This is the end point. Alright, we have gone to completion at this time. So my CO2 will end up being 0.032 and this is 0.06. So I'm going to mark out this as being the level of 0.032, which is the, in this case, the CO2, and I go up about double that to 0.06262, and then they both start at 0, so this guy increases to here, and this guy increases to here. Note that we have a steeper line for the H2O than I do for the CO2 because it got produced twice as fast, and it, in the end, has to increase at a greater rate. Alright, so 1 and 2 we just did. Let's walk our way down here. Alright, so a chemical process contains 0.5 molarity of X and 20% goes to product. So I'm going to do this right here. X, alright, plus, X is just going to Y and Z. So Y and Z. A few things you might want to note about these things is that they do happen to all be, in this case, are going to be aqueous compounds. So we could put a little AQ on them if you'd like. Initial stoichiometric ratio end. I have 0.5 molar here, 0 and 0. If I filled it out, it'd just be minus X plus X plus X, and I don't know necessarily what X is, generally speaking. So this would be 0.5 minus X and X and X. Okay. So, but then they go on to give you a little more information here. They say, okay, so, well, by the way, X is dropped by 20%. So what is 20% of 0.5? It would be 0.2, 20% times 0.5, which is 0.1. So X equals 0.1. So I'll plug in 0.1 here, 0.1, and 0.1. Why are they all the same? Because it's a 1 to 1 to 1 ratio. This is not going to be 0.4, 0.1, and 0.1. Alright. Two other questions which we may want to add on here. Okay. That would be 1A. I would like to know, so this is, what is the equilibrium expression? And B, what is the Kc value? Alright, so, and then I'll do the graph as well. Alright, so and this is not number 4, it's number 3, but the equilibrium expression is just going to be, in this situation, Kc equals the concentration of y, concentration of z, concentration of x. And this is the equilibrium expression. What is the value of the actual Kc? You take your answers at equilibrium and plug them in. So my Kc is going to equal 0.1 times 0.1, or 0.1 squared, over 0.04. This gives me 0.01 over 0.04, and my value ends up being a little bit less than 1. 0.01, yeah, I think that's pretty close. Is that right? It's not 0.04, it's 0.4, so let me make sure I get that number right. 0.4, I knew that was a little off. Okay, so 0.4. So in this case, my answer, K, I believe is what, 0.025? Okay. So remember, if K is less than 1, that means we are reactant favored, which means we have more reactant than we do have product, which is the case in this situation. Alright, so let's do the graph here. I'm going to say that this is the concentration of both X. On my products, let's go with Z and Y. Y and Z. And I'm going to have only one line for them because they can't ever deviate. Start with 0, and I'm always going to gain the same amount. And let's say this represents the concentration of X. And this is the time frame which I hit equilibrium. And I will have, in this case, I want to draw this proportion on this graph. So I'm going to say, let's say this is 0.4 because this is 0.5, and then this is going to be the concentration of X at stalemate. And then we'll say this right here is 0.1, concentration of X. So Y and the concentration of Z. Then all I got to do is, okay, it just continues up. Like that. And this guy drops. There we go. First problem, that problem is done. Okay. Now, let's go to the last one on this page. Alright. Looks like we got some issues here. That's the same one. Alright, let's go down here. Alright, so new problem here. I got A plus 2B yields 2C. So right off the bat, write an equal expression. Kc equals the concentration of C squared, concentration of A, concentration of B squared. Now I'm assuming these are all aqueous compounds. Likely, if you have a workbook page in front of you, that those have been added. That's what I want to do. They both start at 0.5. So let's start an ice table out here. A plus 2B yields 2C. Initial stoichiometric ratio end. This is 0.5, and again I could just they're both 0.5, and then 0 minus x minus 2x plus 2x. I could plug it in like this, and then at some point I'm going to need to be given more information, and they do give it to us. They say that, okay, that the amount of x that A that changes is 20%. So that means as we drop from here to here, x drops down to loses 20%. Or they may just say, by the way, A at equilibrium equals 0.4. They might just tell you that, which is just the same, because 20% of 0.5 is 0.1, and therefore this value here equals 0.4, and this is 0.1, this is 0.2, and this is 0.2. So this is going to be 0.5 minus 0.2 is 0.3, and this is just 2 times 0.2 is I already did that's 0.2. Alright, so it's 0.1. Okay, so in this situation, what do we got here? Okay, one, can I calculate Kc? All I gotta do is take these values and plug them into this expression. So it's going to be 0.2 squared, and then I got 0.4 and then that's A, and then that's the first, and then I have 0.3 squared. Plug it all out, and your K value likely should be about 1.1, I do believe. We calculated out this morning, if I remember correctly. Let's go ahead and let's chart that out here. Let's say I got, in this situation, I want to mimic, I'm going to use this chart here. So I got heat equilibrium at this point. The concentration of A, concentration of B are both going to be the same to start with. And then C is down here. I got a level of 0.2 for C. I got a level of 0.3 for B. And I have a level of 0.4 for A. And therefore, just connect them up. C went from 0 like that. B started like that. And A like that. And away we go. Right here is where equilibrium was established. These would just continue on. Alright. This is the first half of that particular page. You should finish the second half on your own. Thank you very much.